Okay, now we'll look at a torsional pendulum. So here's a torsional pendulum. So a typical example is a disc, and you attach a metal wire from the center of the disc to the ceiling or whatever. And a torsional pendulum is you twist it. So it's twisting back and forth. And in this case, what was the relevant coordinate to measure the configuration of the system was x, which was the distance of the mass from the equilibrium position. Here, the relevant coordinate is what is the angle through which it twists from its equilibrium position. So theta is the relevant coordinate. Okay, and just like Hooke's law, so the torsional, the torque on this disk is minus kappa theta, and Newton's second law for rotational motion is I d square I alpha, which is that. Okay, and you can rearrange these terms. So, and you can rearrange these terms, which I'll let you guys go through. And here is the differential equation describing the behavior of the system. D square theta by dt square plus omega square theta equal to 0. Okay, so let me make sure, let me make a drawing. Let's, okay, it's still broadcasting good. So, okay, this toy is good except that it's unstable. It hangs up on, if you're idle, it'll hang up on you. All right, so here's the torsional pendulum. There was the disc, and there's the reference mark on the disc. Okay, and what you're going to do is the, oops, no. So there we go. We're going to make it oscillate, and theta t. So its configuration is measured in terms of theta t. Theta as a function of time tells you the configuration of the system. And what you saw was the differential equation governing theta is exactly similar to that for this guy. So here is a system that looks totally different from this system, and the differential equation governing the behavior of the two systems is exactly the same. Okay, so this differential and this differential equation are the same. Okay, and again, so theta would be a amplitude over cosine omega t plus phi, again, the solution. Okay. So this guy will oscillate just like this guy will oscillate back and forth. Okay. So a very different looking system, but its behavior is modeled by the same differential equation. Okay, and there is a solution to that differential equation. By the way, kappa is called the torsion constant of the support wire. And as you can imagine, if you hung this by a noodle, spaghetti, kappa would be small. You hang it by a steel wire, kappa would be large. Okay, so that's what. The angular frequency is given by square root of kappa over I. I is the moment of inertia of this object about that axis. The period is 2 pi over I over kappa. Okay, so period for a simple harmonic oscillator. Period for the simple harmonic oscillator was 2 pi m over spring constant, and for the torsional pendulum, t was 2 pi over the parallel of mass is a moment of inertia, and divided by the torsion constant. Okay, so very similar equations. All right, so the period is 2 pi over I over kappa. So here's the next simple harmonic oscillator. It's a simple pendulum, and let me show you the simple pendulum. So here's a simple pendulum. You guys have all seen simple pendulum, and this also, its oscillation is, its position can also be described by a sine or a cosine function. Okay, so this is a simple harmonic oscillator as well. And so let's look at the behavior of this system. Okay, so here the simple pendulum. A simple pendulum is a heavy mass hung by a light string. Okay, and that's the definition of a simple pendulum: a heavy, small mass hung by a string whose mass can be neglected. All right, so there's the weight of the object. The two forces acting on this object are gravity and the tension in the string. And the weight of the object, the gravitational force, can be broken up into two components. This component that's bringing it back to its equilibrium position, and this component that's balancing the tension. So mg sine theta brings it back, and that's equal to, so this is the position of this guy is measured along this arc length. And so there's the restoring force, and that's equal to mass times the acceleration of the object. Now this arc length is written in terms of the length of the pendulum and its angular position theta. So S is equal to L theta. Okay. And anyway, you can so solve this and rearrange it. And L is constant, the length of the pendulum is constant. So theta is what changes with time. So d squared theta by dt squared, d squared theta by dt squared works out to minus GL over sine theta. And for small angles, for angles less than 10 degrees, if you do it in radians, for small angles, sine theta is equal to theta. Okay, you can test that on your calculators, put it in a radian mode. And so 10 degrees would be 60 degrees is 1 radian. So keep a tenth of a radian, and you'll see that sine theta will be equal to theta. Okay, so again, the same differential equation as before. D squared theta by dt squared is equal to minus G by L. You will call that omega squared. Okay. So again, let me make sure we, okay, so for the simple pendulum, d squared theta by d squared plus G over L theta t equal to 0. So G over L is omega squared, we'll call that. And again, what was theta? Theta was, so here was the simple pendulum, there's the equilibrium position. This was theta, theta was that angle, and we were interested in finding that as a function of time. All right, so again, theta, this angle as a function of time is given by that. Again, the same sine or cosine function gives its configuration as a function of time. Okay, the period of a simple pendulum is given by 2 pi L square root of L divided by G. So period is the time it takes to go from one extreme to the other and then back. That's one complete oscillation. Okay, so that's the period of the pendulum. So you could use a pendulum. You can measure the length of the pendulum, you'll know that. And you can measure the time it takes for the pendulum to complete one oscillation and get G, the acceleration due to gravity, from that. Okay. In fact, there's a cute little story when the first astronauts landed on the moon. One of the first things they did was they set a pendulum on the lunar lander in motion. And so people watching at home on TV, they could measure the period of that pendulum. They were told the length of the pendulum. And from that, they could calculate the acceleration due to gravity on the moon. So that was a good experiment for high school students and so on. All right, so next we'll talk about the physical pendulum. Physical pendulum is any object, any solid object that's nailed at that point, so it can oscillate about that point. Now, the only point you can't nail it is at the center of mass. If you nail the object at the center of mass, then it won't oscillate. Okay, so as long as it's not non-central mass point, the object will oscillate. Okay, and so if the equilibrium position would be when the center of mass is directly below the suspension point, and if you move it away from from under the suspension point, this will oscillate back and forth, assuming that's frictionless and so on. Okay, well, if there's friction, the oscillations will die out. But anyway, so here is this guy oscillating. So, and you guys have all seen stuff like this. You guys have seen physical pendulum in grandfather clocks. So you guys have seen grandfather clock, and this will oscillate back and forth. Okay. So that's what we're interested in. So in this oscillation, the torque, the restoring torque, is the weight of this guy times the moment arm, which is d sine theta. Okay. And again, all these terms can be rearranged. Again, we make the approximation for small angle oscillation. Sine theta can be replaced by theta. And so I squared, so the configuration of this thing is given by theta. And that's what we're calculating theta as a function of time. So going back to this slide. So this theta as a function of time. And this is given by, so, and the differential equation governing that theta as a function of time is plus mgd over I, and d is, so if this is the center of mass, this is d, as you can see from the diagram. Oops. D is, there's the center of mass. D is the distance from the point of suspension to the center of mass. Theta t equal to 0. Okay, so there's a differential equation. And we'll call this omega squared. Okay. So again, the same differential equation. So let me summarize. So we started off by studying this mass. Then we looked at a simple pendulum. We looked at a torsional pendulum. We looked at a physical pendulum. So here, 4 different looking systems, very different looking systems. And all their behaviors are described by that same differential equation. Okay, you're just measuring the configuration of the system using different coordinates. Xt for here, theta t here, theta t here, and theta t here. Okay. But all those, the behavior of all these 4 systems, very different systems, are described by the same differential equation. Okay. So that's pretty neat. And so in your differential equation classes, you just learn general techniques for solving various differential equations, which will show up in all kinds of courses that you do as an engineering major. Okay. Okay, so the physical pendulum, the period of the physical pendulum is 2 pi square root of I divided by mgd. Okay, so I is the moment of inertia of this object about that axis. So I can change depending on, so if you nail it here now, then the moment of inertia will be different for this object about that axis. So the period depends on where you nail the, about what point it's oscillating. D is the distance of the center of mass to the axis of rotation. Okay, so there's the moment of inertia. Now, let me tell you a cute story. This is more than of academic interest. So here's an application of it. Okay, so let me, well, I don't draw that good, but okay, so here's my elephant. Here's my rendering of an elephant. Oops, what happened? I don't know what I did. I messed up. All right, well, okay, so let me draw an elephant. So here's my, okay, we'll draw a two-legged elephant, and nobody laugh. Okay. So this, the leg of an elephant can be treated as a physical pendulum, and there is a massive point of suspension. And you can calculate the period of this oscillation for this pendulum. And it turns out that the walking pace, the normal walking pace, corresponds to this. So corresponds to, so half a period gives you one step. And that's the rate at which the elephant walks. Okay? So that's the least energy that you would use when you walk at that gait. And so the animal world, the biological world utilizes that. Anyway, so there's a physical pendulum. Okay. All right, we'll pause now, and I'll let you guys ask questions if you have any, because